Welcome to the lab this week. This week's lab is about dimensional analysis and viscosity. This week's lab has two parts to it. In the first part, we're going to derive the free surface of a spinning column of fluid. In the second part, we're going to use dimensional analysis to derive the relevant pi groups for a problem involving a sphere dropping in an oil. And we're going to use the relationship between those pi groups to back out what the viscosity is of an unknown substance. Let's start with the derivation of the free surface of the spinning column of fluid. So this is the experimental setup. We have a turntable filled with motor oil, and we're going to attach it to a motor which is controlled by this knob, which will turn on, and we'll spin it up. Be careful not to spin it up too high, because then the oil can spill out over the edge and get everything covered in oil. And we see that there's this paraboloid shape in there, and we want to derive the equation for that free surface. So notice there that we're going to be reaching steady state, so this is rigid body motion. So the streamlines will be concentric circles emanating out from the center. And we are going to take as known values our radius of our tank and the angular velocity of the turntable, which we'll measure using an oscilloscope and an optical sensor, which we'll talk about in a bit. So now we've seen the setup, let's go back to the board and try to derive this shape. Okay, so the setup we just saw consisted of a tank with a fluid in it which had a vertex. We're going to note that along the free surface, the pressure is going to be atmospheric pressure. So that's the definition of a free surface. So we're going to try to define an expression for pressure in our tank, and we'll set that equal to PATM. And since this is a cylindrical tank, it's helpful to work in cylindrical coordinates. So we'll define a coordinate system R, Z, and then a theta will be going about Z that way. So P is a function of R, theta, and Z along the free surface equals PATM. And so we're going to try to derive the expression for this pressure. To begin with, let's note what the streamlines look like. So we can look at this from the top down, and we see that they're concentric circles. And we'll say that there's some angular velocity associated with this motion, which means that this velocity at any point along the streamline, of course, is just v is omega r, where r is our coordinate away from the origin. So to begin with, let's note that the pressure along the streamline is going to be the same. So we can do this rigorously by using the Euler equation in the direction of the streamline, so in the Euler S equation. So Euler S, we know, is given by the equation -1 over rho dp ds plus the component of gravity in the S direction. And that's equal to the acceleration along the streamline in the S direction. So we're going to be traveling along the streamline this way. We can look at the acceleration and realize that it's going to be 0 since we're reaching steady state. The component of gravity that's acting along the streamline is going to also be 0, so the gravity vector dotted with the direction of the streamline is g dotted with this streamwise component here, which we'll have, we have to take this point here, we'll have that direction, call that s hat. So that guy will go to 0, which means that dp ds equals 0, which means that pressure is no longer a function of our streamwise coordinate, which means that pressure will not be a function of theta. So we can take the theta dependence out of our pressure equation. So we're looking for P as a function of R and Z equals PATM. And this just is obvious also if you look at it, but this is the more mathematical approach to Y. So to find the pressure dependence emanating outward from the center, we're going to want to use Euler N equation. So anytime we have curved streamlines and we're looking for an equation for pressure across those streamlines, Euler N is an appropriate equation to use. Euler N has the exact same formulation, -1 over rho dp dN plus the component of gravity in the n direction is equal to the acceleration in the n direction. Since we have curved streamlines, we can no longer say that this acceleration is 0. It's equal to negative v squared over the instantaneous radius of curvature. So for a given streamline, we have the s coordinate and then the n coordinate. And so the radius of curvature of the streamline would be, in our coordinate system, just r, which means that the normal coordinate n and this radius r are the same thing. This is usually the case when we have curving streamlines that are circular. So this equation reduces to -1 over rho dp dr. Now g sub n is the coordinate of gravity, the component of gravity in the n direction, which will also be 0, and g, the dot product will be 0, equals -v squared over r. And v is the velocity along the streamline, which we said is omega r. So we get dp dr is rho omega squared r. And then just remember here that the Euler equations, to put them into perspective, are nothing more than a simplification of the Navier-Stokes equations. The Navier-Stokes equations, we don't go through them in depth in ME70, we introduce them, but those are the most general equations of fluid mechanics, and coming out of ME70 it's important to realize what they are and to be able to understand how we get them. So Navier-Stokes is derived by doing momentum balance on a differential fluid element, allowing for viscous forces, pressure forces, and acceleration. And it's a big, long equation in one dimension, and if you want to write equations for three-dimensional flows, you need 3 of them. So you have 3 equations, each of them has a number of terms, and they're all partial differentials, nonlinear, second order, so they become difficult to solve. In order to simplify our lives, we take the Navier-Stokes equations and call it inviscid, and we have the Euler equation. And then we can simplify our lives even further to get the Bernoulli's equation by dealing with steady and inviscid again, and along a streamline, and we're neglecting any frictional effects. We said inviscid. So the general hierarchy of equations goes Navier-Stokes is the most general, then Euler equations, which we've written here in the s and n direction, but they could be written in x, y, and z just as well, or r, theta, and z in that case. And then Bernoulli's equation is the bottom of the chain of those equations. Okay, so we have an expression for dp dr, which is the pressure dependence in r. We know that p is a function of r and z. But we don't have this equation for dp dz yet. We need the pressure dependence on z. So how does pressure depend on height? So our z component, remember, is this vertical position here. So the initial intuition might be p equals rho gh, rho gz. And that is correct, although not quite rigorous enough for what we need here. So rho gh, if you recall, comes from the hydrostatics equation, which gives us the integral of rho g in the z direction, so integral of negative rho g dz, which gives you a p naught plus rho gh, or minus rho gz, depending on the coordinate system. And that itself is a formulation of an Euler equation. So you can think of doing this 2 ways. You can think of it as an Euler equation in the z direction, or you can use Euler s equation and think about a streamline that's dropping from the free surface down to some distance z below the free surface. So the right side is 0. Now you cannot neglect the g component. So g dotted with the s direction is going to be g. And so we're left with just a simple dp dz is equal to negative rho g. Now if we say that pressure is a function of z only, like we did in the hydrostatics part of the class, we could say that p is just p naught plus rho gz, or negative rho gz. But in this case we cannot say that because p is a function of both r and z. So we have this system of ODEs. We have dp dz, and we have dp dr is rho omega squared r. So how do we solve the system of partial differential equations? Well, we'll change markers here real fast. If you integrate one of these equations, let's say we integrate this equation, usually if this was a normal derivative, you'd have a constant of integration out here. So we have p is rho omega squared r plus some constant. However, since the pressure is a function of both r and z, that constant can be a function of z itself. So let's call that constant f of z. So if we check ourselves here, you can still take the derivative with respect to r, and you're left with the correct expression here. Sorry, this is not correct. This is r squared over 2. But anyway, so now if I differentiate this in z, I'll get an expression only in terms of z, and we already have that expression by our first partial differential equation. So dp dz is just f prime of z, which we know is negative rho g. And so this is an ordinary derivative, so we can solve for our function of f, and we have f of z is negative rho gz, and now we add a real constant c, since this is an ordinary derivative. We don't know what this constant is yet. So I can plug my f of z back into my expression for pressure, and I have my p as a function of both r and z is equal to rho omega squared r squared over 2 minus rho gz plus my constant. Now to find the constant, we use our boundary conditions. In this case, we have one boundary condition, which is that at the origin, at r equals 0 and z equals 0, pressure is equal to p atm. We've defined our coordinate system in that way. Which means that if I plug in 0 and 0, I get p atm equals c, which means my constant of integration here for my function f is nothing more than p atm. So this is my general form for pressure in my flow, in my fluid. And I said I'm looking for the free surface, so we're going to set our pressure equal to p atm. So if I do that, I just get the p atms will drop, and I'm left with 0 equals rho omega squared r squared over 2 minus rho gz. And if I want the shape of the free surface, I can solve for z as a function of r, and I'm left with z as a function of r is omega squared over 2g times r squared, which we see is an equation for a parabola, as we expect. And just to check ourselves here, this r, since we're working in cylindrical coordinates, we can convert back to Cartesian by saying that we have some coordinate system in the x, y. This is r, this will be a theta. So our x coordinate is just r cosine theta, and y is r sine theta. If I want to solve for r squared, I can do x squared plus y squared. The cosine squared and sine squared becomes a 1. So we're left with this being just omega squared over 2g times x squared plus y squared. So we're going to try to plot this in Matlab to try to validate our shape. But before we do that, we'll note that we need an omega. Okay? So what we're going to do is try to confirm our analytical expression for the free surface with an experiment. And the experiment will be such that we're looking for, so ideally we'd be able to find the shape at every point along this flow. But a simple way of checking to make sure it's a parabola is to find the height of function at our distance capital R from the center, and see if this height here, z as a function of capital R, matches our experiment and our model. So to perform this experiment, it's not sufficient to simply measure the initial height of our fluid and then measure the new height, because you'll notice that the center drops because mass balance says that we have to. So we'll need to come up with a way of an experiment so that we get this the vertical distance between the origin and the edge of the end of the free surface here. So let's go over to the setup, and remember what we're doing here. We're trying to find an omega and a z, and we'll know what r is at this coordinate here, and we will compare the z that we're measuring with the z that we're going to get out of our model with the given measured omega. Okay, let's go over to the setup. How are we doing on the time? Is it
still have 15 minutes?
15 minutes. Okay, so here we are. I'm going to spin it up, and just note that if I had taken mark of that initial height and this new height, that would not be sufficient to know what the height z is at a function of capital R. What I will do is I'll spin it up fast enough so that the bottom of the free surface, the vertex of my paraboloid, is just touching the bottom of the cylinder. So I'll go spin it up beyond that point. There we go. And then I'll back it out until I'm just tangent with the bottom of the cylinder. That looks pretty good. So now the height that I'm looking for here is just the height from the bottom of the cylinder to this line up here. So I'll take a whiteboard marker and I'll mark it. So now I can turn the thing off and I can measure that with a tape measure, and that would be my height. But we still need omega, we need the frequency, the angular velocity, which we can get from the frequency of these revolutions, which we get from this optical sensor here. So this is shining a laser up at the bottom edge of the turntable. And then the laser is being reflected off of a piece of reflective tape and then reflected back into the sensor. And then that signal that is sent back into the sensor is given to the oscilloscope. And we're going to try to read via the oscilloscope the period of rotation of that turntable, and from that period we can get the angular velocity. So my first thing I'll do is press auto set just so I can see something. And the oscilloscope picks up transitions, so I'm going to zoom way out because I don't want to see the transition, I want to see the whole signal. And I want the period of these signals here. So I'm going to let it go and I'll press run stop to stop it, and then I'm going to zoom in on one of them. And I'm going to introduce cursors, so there can be two lines, they can be moved around the screen. And I'm going to measure the distance between that point and that point. And along the right side you see a delta. Delta says it's 416 milliseconds. So now we know the period of the turntable, 416 milliseconds. So we have the period, so we'll get angular velocity, and we know the radius of the cylinder, which is 9.5 centimeters, and we've measured the measured value of z at a function of capital R. So z at the edge of the cylinder. And that measurement will be 11 centimeters. So I'm looking to recreate that using our model. You can do this really quickly. Z at capital R is equal to omega squared over 2g times capital R was 0.095 squared, and omega is 2 pi over the period, which is 2 pi over 0.416. We said there was a 416 millisecond period, which I can do on my calculator. So let's do that really fast and then we'll tell you what we get. Okay, so we've done it on the calculator and we get, it's a 10.5 centimeter height, which compares pretty well to our measured 11 centimeter height. So that is good. Now let's try to use the angular velocity that we measured, and we're going to use Matlab to try to plot the shape of the entire paraboloid using the surf command. So I'm going to write up some code on the board, and then you're going to go and in Matlab recreate this code and try to give us the shape of the free surface. Alright, so the first thing we're going to want to do in Matlab is to just define some constants. So we'll define G, we'll define omega, which we just measured, we'll define capital R, which is 0.095 meters. It's always good to write your units out there. And eventually we want to plot using the surf command. So surf creates a surface where you give it Cartesian coordinates x, y, and z, where z will be the height at a point x, y out from the origin. So let's say our coordinate system starts here. What we'll want to do is we'll want to create a series of points in this domain, within this radius, this capital R radius. And we're going to want to apply our equation for the free surface to every single one of those points. So we can say z equals, we had omega squared over 2g times x squared plus y squared. And we'll just plot x, y, and z, but we have to make sure that we have a vector or matrix of x and y's such that we have points along our domain, everywhere in our domain. So we'll use the mesh grid command for this. Now mesh grid, what it does is you give it two vectors which represent the domain in the two x or y and y dimensions that you're trying to plot. So we could give it a vector of x's from negative r to r and y's from negative r to r, and it would create a mesh of points in between those. But that's actually not what we want, because that would give us points out here which are outside of our domain. So what we can do is we can do mesh grid with cylindrical coordinates here. So we can be getting r points and theta points, which will give us a ring, a bunch of concentric points within our domain. So we'll be getting r and theta out, and then the domain of our radial component will be from 0 all the way to capital R at increments of something yet to be determined. And then the theta direction will be from 0 all the way to 2 pi, 1 revolution. And the increment here, ideally I would know how many points I have, so I can specify the number of points within my one axis of my domain. So let's say we want 50 points, so I'll call that number n. And I want 50 points in both the r direction and the theta direction. So then my increments are going to be r over n and 2 pi over n. Okay, so now we have r and theta, but we know we want to plot in Cartesian, x and y. So I need to do some conversion between r and theta. And of course this is just r, and it's going to be a dot times cosine theta, and r dot times sine theta. And be careful about the dot squares over here, because x and y are both going to be vectors. Great, so we can perform this in Matlab, and we're going to get a nice plot of our surface. And to make the problem more physical, or the plot look more physical, we can make the axes the same dimension in both x and y and z. So we can use the axis equal command. Otherwise, the plot will be scaled in a non-physical manner. Alright, let's go look at the plot. Great, so here's our plot of our free surface. We can rotate around and we look inside, and it definitely looks like a paraboloid. And we note that given our angular velocity we measured, our predicted value looks like about 10.5 or 11 centimeters, which is what we saw before in our calculator. So the surf command is pretty handy, mesh grid is handy, and now you guys know exactly how to plot 3D surfaces. Great, so we just concluded the first part of this lab. In the second part, we're going to use Buckingham pi to relate pi groups, to find relevant pi groups in a problem that we can use to solve for the viscosity of an unknown substance. So first, let's look at the problem at hand here. We're going to drop spheres through a column of oil, and we're going to try to solve for the viscosity of this oil, and we're going to posit that the viscosity, the drag force on the sphere will be a function of viscosity, which means that we're going to want to write an expression involving drag force. So let's just solve for let's just draw a free body diagram for this body. It's going to be some gravity force, it's going to be some drag force, and there's going to be some buoyant force. And we're going to say this thing has reached steady state, so it's going to be non-accelerating. And we can define our coordinate system with y going upward. And we know, let's say we know the density of the sphere and the volume of the sphere and the diameter of the sphere. And we'll say it's submerged in some fluid with density rho. So we can do our force balance in the y component. Negative mg plus fd plus fb equals ma. And we're saying we're going to reach terminal velocity, so the acceleration is 0. We can write an expression for the buoyant force. So the buoyant force is the weight of the fluid that's being displaced by our object, which we know is just the density of the fluid times g times the volume of the sphere. So this becomes negative. So the mass of the sphere is going to be rho sphere v sphere times g plus fd plus the buoyant force is rho g times the volume of the sphere. And this equals 0. So this sort of sets up the problem here. And we need to get an expression for the drag force involving viscosity. And then we're going to try to back out what viscosity is. So think of the following process as a homework or exam problem, where someone asks you, derive the relevant pi groups for the expression for what the drag force of a sphere being submerged in a moving fluid would be. So Buckingham pi is nice because otherwise you'd have to say that the drag force here, so we'll say FD, is some function of some parameters. Now, the part of this process requires some practice, where you have to intuit what parameters are going to be important in this problem. So the physical parameters here, which we think might be important, are going to be the viscosity of the fluid, because if you think of this as dropping a sphere through honey versus air, you're going to have different drag force. The density of the fluid might matter. Some characteristic length, some size of our object in the fluid will matter. A BB and a bowling ball have different drag forces on them. So let's call that the D, the diameter of the sphere. And then the velocity of the moving fluid will probably matter. So that'll be a V. So this is sort of our first guess at what the drag force might depend upon. And this is a lot of parameters. What we want to do is we want to be able to find the drag force using fewer parameters and make it a more general problem. So if I were in the business of measuring drag forces, I could go ahead and make a bunch of spheres and put them in a bunch of different fluids with different densities and viscosities and subject them to different velocities. And I could hold each one of these things constant and vary one variable, and I'd have a bunch of different relationships between drag force and viscosity, and drag force and density, and drag force and velocity. And that seems like a hassle. And there's a better way of doing this, which is to collapse these variables into non-dimensional numbers or groups, and then use the relationships between non-dimensional groups to get back out what the relationship is. So what we can do is we can convert this into a function of two pi groups. So we'll have some pi1 is a function of some other pi group. And in general, there could be other pi groups in here. If we added more variables that we think our problem depends upon, there's going to be more pi groups that are going to be related. And the functional dependence here is, well, first of all, it's not predicted by Buckingham pi. This needs to be done by experiment or other theory. But this functional dependence is universal. This is a fundamental relationship. So by doing an experiment where you can actually derive the relationship between the two pi groups, that is worthy that's an important relationship. That is a universal physical law or rule that you can work with. So in this lab, what we're going to try to do is derive the pi groups, and then we're going to use a relationship that already exists, that someone else has already taken experiments on and already done the derivations for. But we need to derive the pi groups that are relevant to begin with. So what are the pi groups relevant to this problem? So the first step in finding pi groups is to identify the parameters of importance, which we've done. So I'll write this down as a cookbook. Identify relevant parameters. The second step is to determine how many pi groups we need to be looking for. And to do that, we need to express each relevant parameter in terms of their fundamental dimension. So the second step is to express parameters in terms of fundamental dimensions. To take a step back here and look what we're doing here, we're just trying to find groupings of these variables, 1, 2, 3, 4, 5 of them, that create a number that is non-dimensionalized. So we're going to choose some of these variables that are going to be the variables that we're going to use to non-dimensionalize other ones. You'll see this in a second. So let's do this part first. So I'll create a matrix here with my dimensions. I have my parameters, f, d, I have mu, I have rho, I have v, and I have d. And I'll note that the only relevant parameters here, relevant fundamental dimensions are going to be mass, length, and time. So we can have mass, length, and time on this axis. And I'll create this grid. So my drag force is a Newton kilogram meter per second squared. So 1 kilogram meter per second squared. Viscosity, you can derive from the shear stress equation, tau equals mu du dy. You get kilograms per meter per second. I encourage you to do this exercise on your own because this is something you'll have to do later. Density will be mass per volume, so 1, -3, 0. Velocity is length per time, and then diameter is just length. So in order to find non-dimensional groups, I'm going to need, first I need to figure out how many non-dimensional groups I need. And the answer to that is, so number of pi groups equals the total number of relevant parameters in your problem, so 5. So number of parameters minus the number of dimensions that are spanned by our problem. So we just have mass, length, and time. I'll say number of dimensions. And just for reference, the fundamental dimensions that exist, to my knowledge, are mass, length, time. We have temperature, there's charge, and there's lumen, which is the measure of brightness. And there might be others too, which I'm not aware of, but those are ones that I've seen. So in our case, we have 5 parameters minus 3 dimensions, so we'll have 2 pi groups. So we're going to be looking for pi 1 and pi 2. And of course, note here that we could be adding other dimensions that are other variables that our problem might be relevant. That might be relevant for our problem, such as the temperature of the room or the atmospheric pressure. And that would be fine. We just introduce more pi groups. But what would end up happening is, if they're not relevant, and we've made a mistake, then the functional dependence on pi 3, for example, if it existed, would be minimal. It would be some small number times pi 3, for example. So that will drop out in our experimentation. We do not have pi 3 because we're being smart about which parameters we pick that are of importance. Okay, so the next step is we're going to choose some of these parameters, to non-dimensionalize another one. So we're going to take a grouping of these parameters that need to be non-dimensionalized. So I'm going to choose some ingredients for this non-dimensional number. And to do that, you need to choose parameters that span all the dimensions that we're working with. So I'm going to call those things repeating parameters that we're choosing. So choose repeating parameters. And you're going to use these to non-dimensionalize every other parameter you have in your problem. And the number of repeating parameters is the same as the number of dimensions, fundamental dimensions. So 3 of them. And as a good choice of repeating parameters, if you know a certain pi group, such as Reynolds number, you can choose parameters that are in that pi group because that will make your life a little bit easier in deriving that pi group. So I'm going to use rho v and d because Reynolds number is rho v d over mu, and that's a good choice. So you could choose other ones too as long as they span all the dimensions and mass, length, and time. And also it's nice to have the whatever variable you're looking for. That should not be a repeating parameter because you're going to want this with an exponent of 1 in front of it, or raised to the exponent of 1, just so we have an explicit expression for the drag force. So I'm going to choose rho, v, and d. And then we're going to try to non-dimensionalize our other 2 variables in terms of these repeating parameters. So pi 1 will be, for example, fd times rho to some power a, v to some power b, d to some power c. And this thing should be non-dimensionalized. So this will go to, if we do it in dimension form, some mass to the power of 0, length to the power of 0, time to the power of 0. So now we just simply express what each of these variables are in terms of their fundamental dimensions. So this becomes mass, length per time squared, this is my drag force, times density, which is mass to the a L to the negative 3a times velocity, which is length to the b, t to the negative b, times diameter, which is L to the c, and this equals m to the 0, L to the 0, t to the 0. So now I can add up my exponents, and I have three equations, one for mass, one for length, and one for time. So balancing my exponents in mass, I have 1 from that plus a equals 0. For length, I have 1 minus 3a plus b plus c equals 0. And then for time, I have negative 2 minus b equals 0, which yields a equals negative 1, b equals negative 2, and c equals 1 minus 3 is 4, minus 2 is 2, minus that is negative 2, which means that my pi group is equal to FD divided by rho v squared d squared. And this is completely 100% correct. However, we want to make this pi group look like a pi group that already exists, so a conventional pi group. And we know that this is of the same form as the drag coefficient, c sub d. So we can multiply this pi group times any constant we want, and it will remain a pi group. We can raise it to some other constant, and it will remain a pi group. We can even add constants to it, and it remains a pi group. But in order to use the functional dependencies that someone else took experiments for, we want these pi groups to be known quantities. And so the drag coefficient c sub d is defined as the drag force over 1/2 rho v squared times a, which is the frontal area of our object. We've seen this in previous labs. So this is pi 1, let's get pi 2. So we can do the same process for pi 2, just by non-dimensionalizing mu instead of fd. But we can also recognize something, which is that we have mu, rho, v, and d. And we've seen Reynolds number a bunch of times. So by now in the course you should be familiar with what it is and how to recognize it. So we can just pull that right out. We can say pi 2 is equal to Reynolds number, which is defined as rho v d over mu. And you can of course derive this the same way. So now we have our two pi groups. We don't have the functional dependence, but we know that there will be one. So we can say that c sub d is some function of Reynolds number. Great. So from now on, we have to go use another process to find this functional dependence. So it turns out for a sphere being dropped in a fluid, there are measurements for this. And this is a pretty cool result. It means that you can take spheres of different diameters in different fluids and different densities as long as the Reynolds number stays the same. And the drag coefficient should be the same. So the result from these experiments looks like this. So this is the log of the Reynolds number, and this is the drag coefficient. It has this shape, linear in the early Reynolds number regime, and then there's this bump over here for turbulence. And in the low Reynolds number regime, this becomes a linear line. And the experiments show that c sub d is equal to 24 over the Reynolds number for low Reynolds number much less than 1. Okay? And we're going to be using this low Reynolds number regime since we have extremely high viscosity fluid, oil, and our velocity is going to be small, and our diameter is going to be small, so we have low Reynolds number. And this is called Stokes flow, by the way, which we saw in lab 1. We did that thought experiment with the honey traveling around the sphere. We labeled that Stokes flow, and it's the same thing here. Now, given that this is such low Reynolds number, it's very, very laminar. So the flow around this object is very well defined. It just comes in and does not separate around our sphere, and just comes right around it. So what we can actually do is we can write the Navier-Stokes equations around this sphere, taking into account viscosity, and we can integrate the pressure over the entire area to numerically get what to analytically get what the drag force will be. And what we pull out from Navier-Stokes equations, and this you have to take my word for it, is that the drag force on this sphere is equal to 3 times pi times the viscosity of the fluid times the velocity, this is some v, times the diameter of the sphere. Now keep this in mind, we're gonna get this using our experiment in a second. I'm just telling you that there's two ways of getting out what this relationship will be. One is experiment and one is with theory. So, given that this is true, I'm going to plug in for what the drag force is, the drag coefficient is, and what the Reynolds number is, solve for the drag force, and then plug the drag force back into our problem that we're dealing with. So, coefficient of drag is Fd, which is equal to 24 over the Reynolds number, so mu comes to the top, rho Vd on the denominator, and I have 1/2 times rho v squared. And then the area of our sphere will be pi r squared, so that's pi times d squared divided by 4. Now this should equal this, so let's confirm that this is true. We get 24 over 8 is 3, that's good. We still have a pi, that's good. Our mu remains in there. Our v squareds will cancel with a v down there, so we have 1v, and we have a d up here. So, confirmed. Cool, so now we have our expression for drag force, and indeed it has a viscosity term in it, which is what we want to solve for. So I can plug this viscosity, this term for drag force, back into our equation here, and I'm going to solve for viscosity, and I'll get that. So let's see, Fd is v sphere times g times rho times rho sphere minus rho. Sorry. Yes, that's right. Okay, and then of course this is equal to our 3 pi mu v d. So then mu is equal to v sphere is going to be 4/3 pi v cubed over 8 times g times rho sphere minus rho divided by, I've got 3 pi v times d. And I can clean this up just a little bit by saying that this is equal to the pi's drop. This becomes a 1, this becomes a 2, so that's 6 divided by 6 times 3 is 18. So I have this becomes a d squared. So I have d squared g times rho sphere minus rho divided by 18 times v. And this, of course, is the terminal velocity since we said the acceleration was 0 to begin with. So this is mu. Now, what we can do in order to solve for what mu is we can take measurements for these quantities for any type of sphere. This is general for any sphere in any low Reynolds number flow. And I should get the same value for mu. So this is pretty cool. We used Buckingham pi to derive the relevant pi groups. We did an experiment, or we used experimental data to relate those pi groups, and then we plugged back into our initial problem to find out how to run an experiment in our experimental setup to solve for viscosity. So let's go to the experimental setup right now and look at what we're going to be doing. So here we have two columns of fluid. So this is an unknown fluid. This is motor oil. They're both oils. We're going to be dropping spheres. So this is one of our spheres, a red sphere. And this is super exciting, so watch very carefully. Drop it in there and let it fall. Notice how it reached terminal velocity pretty quickly. And so we're going to measure the time it took to travel between this line and this line, which is exactly 1/2 meter. And that will give us a measurement for terminal velocity. Given that measurement, and given that we can measure the diameter of these spheres, and we know the density of these spheres because we bought them, we can plug in for our equation for viscosity and then solve for the viscosity of this liquid. And of course note that we have different spheres to be working with, and they should all give us the same answer for viscosity because we used Buckingham pi to find how the pi groups. This should be problem independent. So what you're going to do is you're going to take each of these three spheres. The metal spheres are heavy enough that they don't reach terminal velocity. So we can see what happens with these ones. It just drops in pretty quickly. So you're going to take the red, yellow, and clear spheres. You're going to measure terminal velocity values in both fluids for each type of sphere. And if I were you, I'd take 2 or 3 measurements per sphere, so per type of sphere. And then you're going to calculate the viscosity of this fluid and the viscosity of this fluid. And I want you to report back to me what these viscosities are. So we've run our experiment, we've gone back to Matlab, and we've done some calculations, and we find that the viscosity value for the dark fluid, which is motor oil, we got mu motor is 0.22 kilograms meter per second. We found the viscosity of the other fluid, which turns out to be corn oil, is 0.11. And we noticed that we got the same value using each different type of sphere. So in summary, this lab was about reviewing Euler equations using the viscosity turntable, where we derived the free surface of the spinning fluid in a cylinder. And then we used Buckingham pi theorem to find the relevant pi groups for our sphere dropping in a fluid. And we used Buckingham pi, and then we used those pi groups and a pre-existing relationship to solve for the viscosity.